And hello everyone, welcome to this webinar on reducing societal impacts from hazardous weather and other environmental phenomena, the third of 5 seminars in the NOAA Science Report seminar series. The next seminar in this series will be held on March 23rd at 3 p.m. Eastern Time. The sponsors for this seminar series include the NOAA Research and Development Enterprise Committee, or RDEC, and the NOAA Central Library. And I want to thank the NOAA library staff, especially Katie, for their valuable assistance with the seminars. I am Jeff Wielgus, and I am the Performance, Risk, and Social Science Office representative on the RDEC, which is a cross-office committee of the NOAA Science Council. The RDEC is responsible for the development of the NOAA Science Report with input from contributors across NOAA. The NOAA Science Report is an annual report that highlights NOAA's scientific accomplishments for the year and reflects NOAA's research priorities. The 2021 NOAA Science Report spans the entire range of NOAA's mission, with more than 60 stories that represent the accomplishments of NOAA employees as well as NOAA's partners. The report will be released shortly on the NOAA Science Council website, so please stay tuned. Today, we welcome 5 speakers featured in the 2021 NOAA Science Report, whose science addresses reducing the societal impacts of hazardous weather and other environmental phenomena. The full bios for our speakers today can be found in the website description of the seminar, so I will just provide the names and affiliations in order to save more time for their presentations. So our speakers are Dr. Amy Butler, research physicist with NOAA Chemical Sciences Laboratory; Kyle Hilburn, research associate with the Cooperative Institute for Research in the Atmosphere; Dr. Vijay Tallapragada, chief of the Modeling Data Assimilation Branch, NOAA National Weather Service Environmental Modeling Center; Dr. Avichal Mehra, chief of the Dynamics and Coupled Modeling Group with the NOAA National Weather Service Environmental Modeling Center; and Mark Suttle, Merhab Program Manager with NOAA National Ocean Service, National Centers for Coastal Ocean Science. Each of our 5 speakers will give an 8-minute presentation, and after all of the presentations, there will be a question and answer session. So now I would like to invite Dr. Amy Butler to begin the presentation by telling us how frigid Arctic air outbreaks may be predictable. So, Amy, I will go ahead and turn it over to you.
Okay, thank you. So my name is Amy Butler. I'm from the NOAA Chemical Sciences Laboratory, and thank you for inviting me to speak about our contribution to the 2021 NOAA Science Report seminar series. Today I'm going to be talking about how winds in the stratosphere, which is a region 10 to 30 miles above us, can provide windows of opportunity for forecasting winter weather and extremes. And so one example, which I'm showing here, is the high impact cold air outbreak over the central United States in February 2021, which was preceded 6 weeks earlier by a major deceleration and slowdown of the winds in the polar stratosphere. And these winds are referred to as the stratospheric polar vortex. And so you can see on the video on the left a series of images which show the polar vortex air swirling around in the stratosphere in the weeks leading up to this cold air outbreak over the US. And so while this event was likely predominantly driven by specific weather conditions, the disruption in the polar vortex above likely helped to provide some of the key ingredients that made this weather event transpire, and more importantly, made it potentially predictable at much longer lead times. So it's well known at this point that winds in the polar stratosphere can influence weather. So during winter in the Northern Hemisphere stratosphere, sometimes the normally counterclockwise winds rapidly slow down and reverse direction, which is called a sudden stratospheric warming because the stratosphere also rapidly warms when this happens. And these circulation changes in the stratosphere can have a downward influence on the surface, which persists for weeks to months afterwards. And this is shown on the plot on the left, which shows how the geopotential height anomalies evolve on average after all the sudden stratospheric warmings in the historical record as a function of altitude. And so one analogy I like to use is to imagine a bowl of water in which you start to stir in one direction with a spoon. And so the water throughout the bowl all starts to move in the same direction. But now imagine you insert the spoon just a couple of inches into the top of the swirling flow. And so the water in the top layer is going to crash into the spoon and stop swirling. And the layers in the bottom of the bowl will keep moving, but start to slow down as well due to the influence of the water above it. So this isn't a perfect analogy because in reality the mechanisms are different, but it gives you an idea of how the atmospheric flow is all connected from the top of the atmosphere down to the surface. So at the surface, the buildup of atmospheric mass over the polar cap during this event results in a shift of the North Atlantic jet stream equatorward. And this basically allows air that's been sitting over the Arctic, very cold air, to spill out into the mid-latitude regions, but particularly over Europe, Asia, and the eastern United States. And in the middle plot, you can also see that there are anomalous regions of anomalous warmth over Greenland and subtropical Asia and northern Africa. And there are several clear examples of recent sudden stratospheric warmings that have had a big impact on weather, such as the February 2018 sudden warming, which led to a winter storm that was so impactful it was given the name Beast from the East, and snow was seen as far south as Rome. And so the persistent influence of these events on the circulation and surface below makes them a main source of wintertime predictability on S2S timescales. So in the 2021 NOAA science report, we shared results from new research out in Communications, Earth, and Environment on stratospheric drivers of extreme events at the Earth's surface. This was led by Daniela de Meissen at the University of Lausanne and myself. And the goal of the study is to highlight that these disruptions in the polar vortex, or these sudden stratospheric warmings, not only influence the likelihood of cold air outbreaks, which is how we typically hear about them in the news, but are also linked to a wide range of other extremes, which include things like ice melt over Greenland, sea ice changes, heat over northern Africa, and flooding over the Iberian Peninsula. And further, these weather extremes have broad societal impacts, including on health, mortality, transportation, agriculture, and energy. And in a separate but related study, we showed that week 3 to 4 predictive skill for near surface temperature increased over many different Northern Hemisphere regions for forecasts initialized during sudden stratospheric warmings compared to forecasts when stratospheric winds were near climatological values. And so these are showing the increases in skill that occur in many of the regions in the red bars, and in the blue bars you can see where the skill has actually decreased. And interestingly, one exception to this is over Europe, where we typically see actually the biggest impacts from sudden stratospheric warmings. And so our interpretation of this is that Europe is right at the jet exit region of the North Atlantic jet stream. And so there's uncertainty in the forecasted jet, which might actually be enhanced after sudden stratospheric warming events that can lead to big uncertainty in the temperature response downwind of the jet. Going back to our study on extremes, we also reviewed recent studies that found that stratospheric influence on extremes extended beyond just the role of sudden stratospheric warmings in the Northern Hemisphere, but also includes a number of other types of stratospheric variability that have broad impacts on the troposphere. For example, in 2019, the Southern Hemisphere polar stratospheric winds showed unusual rapid deceleration, which was linked to a minor warming of the stratosphere. And this subsequently contributed to intense hot and dry conditions over Australia that led to one of the worst bushfire seasons on record. Another example is in spring of 2020, the Northern Hemisphere polar stratospheric winds were extremely strong, and that was linked to record hot conditions over Siberia. And finally, winds in the tropical stratosphere related to the quasi-biennial oscillation have been linked to extremes both locally and afar due to atmospheric teleconnections. So one of the additional outcomes of this work is that some of the stratospheric experts across labs at NOAA started to realize that the old NOAA graphic describing the polar vortex was not as clearly drawn or worded as it could be, and it was leading to some miscommunication about what the polar vortex is in the media and even in other science publications. And so Stan Benjamin at NOAA GSL originally approached me about revising the schematic, and we put together a team to assess and update it, the final version of which is now shown here, and it's on the web. And this was published along with a climate.gov blog post written by Rebecca Lindsay, linked here, explaining the polar vortex. And the schematic now more clearly separates the stratospheric polar vortex from the tropospheric jet stream, and also more clearly shows the differences between a strong and stable polar vortex and a weak disrupted vortex when there's a sudden stratospheric warming. So to conclude, winds in the polar stratosphere are increasingly recognized as being linked to weather extremes. And more broadly, variations in the stratosphere lead to long-lived, by which I mean weeks to months, effects on the climate system, which allow us to predict weather extremes weeks in advance and provide time for preparation and response. And while I didn't have time to get into it here, in more recent work, we've investigated state-of-the-art S2S forecasting systems and found that they still have a large number of stratospheric biases, and some of them have missing processes. For example, they don't simulate a quasi-biennial oscillation, which may mean that we're not obtaining the forecasting skill theoretically possible from stratospheric information. So with that, I'll say thank you, and please feel free to ask questions at the end. Thanks.
Thank you, Amy, for your excellent presentation. And everyone, as Amy said, please remember to add your questions to Amy and the other speakers to the chat box, and they will be answered in the Q&A session after the presentations. Our next speaker is Kyle Hilburn, who will present on how machine learning using satellite data aids weather prediction. Kyle, I'll turn it over to you.
Thank you. My name is Kyle Hilburn, and I'm a research associate at CIRA. If you want to be able to forecast severe storms, first you need to know where those severe storms are. Radar data are the gold standard for doing that. And as you can see in the figure on the left side, over the eastern half of the United States, we have very good radar coverage. But over the western half of the country, there are some gaps in that radar coverage. And over ocean regions, we have no radar coverage at all. So today I want to talk about applying machine learning to satellite data in order to provide radar information everywhere in order to initialize severe storms in weather prediction models. I'd like to acknowledge my collaborators and co-investigators, Chris Kumaro and Steve Miller at CIRA for their vision and their expertise in remote sensing. Emma Ebert-Uphoff, who's in the Electrical and Computer Engineering Department at CIRA, who's helped out with the machine learning. Yunjin Lee at CIRA, who developed the vertical profile model. Alex Liberdoni at CIRA, who helped develop the original data set. Amanda Back at the Global Systems Laboratory, who performed retrospective simulation. And Stephen Wygant and Curtis Alexander at GSL for their vision and expertise in data simulation. So the high resolution rapid refresh, or HRR model, which is shown in the green box in this diagram, is NOAA's current operational system, and it does use radar data to initialize storms. But NOAA is updating its numerical weather prediction models to use the Unified Forecast System, or UFS. And so HRR will be replaced by the Rapid Refresh Forecast System, RRFS, or RUFUS, which is shown in this yellow box here, this large, very large yellow box here. You can see much of that box doesn't have any radar coverage at all. Therefore, geostationary satellite products will be key to initializing and assessing the RUFUS system. So this is where the GOES-R series comes in. The GOES-R series provides substantial new capabilities. Those include 3 times more spectral resolution, 4 times more spatial resolution, 5 times more temporal resolution, and lightning mapping. So the hypothesis behind this work is that by leveraging the power of machine learning, GOES-R's capabilities can be used to provide radar everywhere for initializing convection in high-resolution models. So what is machine learning? Machine learning is simply a collection of powerful nonlinear statistical methods. The goal of machine learning is a trained model, which you see here in the center of the diagram. And there's 4 components that have to come together to make a trained model. First is the data set. Machine learning is all about the data. Ultimately, machine learning can only learn what's in the data set. So that's the most important component by far. The second component of this is the loss function. This gives the mathematical form to what's being minimized and actually controls what's being learned and what the model is focusing on. Then there's the model architecture. That determines how the information is learned, whether it's using a dense architecture or a convolutional architecture or recurrent architecture. And then finally, there's the optimizer, and that actually does the work of the learning, where learning is iteratively adjusting weights in a model. So when those things come together, you can form a trained model. So the methodology today is called Gremlin. That stands for the Goes Radar Estimation via Machine Learning to Inform NWP. You can see in the diagram for Gremlin, it looks sort of like the letter U, and it's in the class of models called UNets for that reason. You can see these blue arrows in Gremlin. These are convolutional layers. These layers capture the information content and spatial patterns and gradients in the imagery. Then you see yellow or green, red and yellow arrows, and those are pooling and upsampling layers. And the purpose of those layers is they capture multi-scale information that's present in the imagery. So Gremlin is performing data fusion, combining advanced baseline imager radiances with geostationary lightning mapper lightning. And Gremlin is performing image-to-image translation. So the inputs to Gremlin are GOES fields, and the outputs are multi-radar, multi-sensor fields. So the first key insight of this work is the importance of something I'm calling spatial context. In panel 1, I'm showing GOES brightness temperature. The color scale is inverted so that the red and purple colors are the very coldest brightness temperatures. In panel 2, it shows a version of Gremlin where I've turned the spatial context off using 1-by-1 filters. And you can see that when I do that, Gremlin can still identify cloud versus no cloud areas, but it can't see the strong radar echoes. In panel 3, I've turned the spatial context back on. You can see now it matches MRMS truth very well. And you can see that these areas of higher radar reflectivity identified by Gremlin, they don't simply correspond to areas of cold brightness temperatures, but areas of sharp brightness temperature gradients as well. So it's the ability of convolutional neural networks to utilize spatial context, by which I mean multi-scale image gradients, is essential for this application, and it offers breakthrough improvement in skill compared to traditional non-machine learning approaches. So on this slide, I'm presenting results of a retrospective simulation that Amanda Back performed at GSL. This is using the experimental Rufus model. Panel 1 shows MRMS. This is the usual input to the Rufus model. And the bottom panel, panel 2, shows Gremlin. So Amanda replaced the usual MRMS input with Gremlin input. Panel 3 shows the MRMS forecast, and panel 4 shows the Gremlin forecast. And you can compare those with MRMS truth, which is 1 hour later. And you can see that even though this is an area that does have good radar coverage, Gremlin actually forecasted this convection over southwestern Oklahoma better than MRMS did in this particular example. Now, it's not just that one example, but these improvements were found to be consistent during the 1 week experimental period. These are figures that show a skill score called the Critical Success Index, or CSI, where higher values are better versus forecast lead time. The upper panel shows over all of CONUS, and you can see that Gremlin, which is in the purple line, MRMS in the blue line, are both much better than no initialization at all, which is the red line. Now, over the Western United States in the lower panel, you can see Gremlin in the purple line is consistently outperforming MRMS because this is an area that has limited radar coverage. So to conclude, this work has demonstrated that applying machine learning to satellite data provides new information to improve weather forecasts. This work is important because it provides information in areas without radar coverage. It's relevant to the severe weather hazards faced by society, and it is supporting a weather-ready nation. So our next steps are something called interpretable Gremlin, where we build in explainability right from the start to obtain a transparent and trustworthy model. And we're also performing additional testing of Gremlin in the Rufus model at NOAA GSL. Thank you very much.
Thank you, Gal, for a great presentation. Our next speaker is Dr. Vijay Tallapragada, who will tell us about NOAA upgrades to a global forecast system. Vijay, please take it away.
Yeah, thank you. Good afternoon, good morning, everybody. My name is Vijay Tallapragada. I'm the Chief of Modeling and Data Assimilation Branch at NOAA's Environmental Modeling Center. and thanks for the opportunity to present at this NOAA Science Report seminar series. So the topic is on the global forecast system, how we are making upgrades to it, and what went in the most recent upgrade in 2021 that is part of the NOAA Science Report. Global forecast system is probably one of the most used forecast system or modeling system in the whole world. This is the only model that provides data free of cost to any stakeholders, anybody who's interested in weather forecasting, research, operations, and so many applications that are driven by the global forecast system that it is a cornerstone of NOAA's operational modeling systems. And this goes periodic upgrades every year or every few years to introduce new science, new technology that generally leads to forecast improvements that are substantial, that we justify these upgrades to the modeling system. So the next few minutes, I'll be talking about what went into the GFS version 16 and slightly introduce the concept of unified forecast system for medium range weather. What are the benefits of these upgrades, and then some ongoing developments and future plans. So improving operational global model forecast is the motivation here to be the #1 in the world. We have to strive to introduce the advanced science and technology that can be transitioned into operations. And what we did in version 16 of the global forecast system that was implemented in March 2021 is to increase the vertical resolution and also raising the model top from about 54 kilometers to 80 kilometers. This is almost like doubling the resolution in the vertical that provides more discretized information that can be gathered in the vertical as the atmosphere goes up into the stratosphere. We also made several changes to the physical parameterizations that go into the forecast model, particularly the gravity wave drag parameterization, the convection scheme, and the primary change actually was for the planetary boundary layer scheme. We introduced a new scale-aware turbulent kinetic energy-based hybrid eddy diffusivity mass flux parameterization scheme that resolves the boundary layer and the surface physics much more accurately to improve the forecasts near the surface. We also made several changes to the data assimilation system where we are now including more observations than before, including from the newer satellites that were recently launched, including GOES, geostationary satellites, as well as the polar orbiting satellites. And we also introduced the cosmic radio occultation data and aircraft data and so many more that went into this GFS version 16. Another major enhancement to GFS version 16 is coupling to the global wave model. And this wave model is actually separately run in the past. Now it is combined with our global forecast system for the atmosphere, and it is providing a continuous wave forecast along with the atmospheric weather forecasts such that the marine stakeholders can benefit from it. Some of the examples from the GFS version 16, we improved the forecast across the globe with improved consistency. We improved the frontal positions and heavy precipitation, particularly over the continental United States. We improved the temperature forecast in the lower troposphere. A lot of the cold bias that we saw in the wintertime, that was mitigated. We also had significant improvements for the tropical cyclone formation, the tracks, intensity, and the structure. And we also have improved the stratospheric forecast. The example I'm showing here is a comparison of what was there in the past compared to the new model. This is for a bomb cyclone that was impacting the West Coast in 2020. And the GFS version 16, the new model, accurately captured the precipitation that was impacting the West Coast more accurately compared to the previous version of the model. And these are typical examples that we see for almost all significant weather events. In the tropical cyclone forecast, this is a significant improvement. Hurricane Dorian that was impacting the Florida Panhandle and eventually moved into the mid-Atlantic states. the new model actually has a better representation of the storm structure and also accurately represented the storm missing the direct hit to the Florida, whereas the old model that was operational at the time was showing a completely different picture where the storm was making a landfall on the west coast of Florida. And the differences here that show how big the impact could be. And this leads to improved preparation for forecast evacuations and also managing the economic losses due to evacuations. So this is something that the Hurricane Center absolutely would love to have improved accuracy from our global models. Another example here I'm showing is in terms of the general weather prediction. The frontal boundaries are important for transitioning from either cold to wet, cold to warm, or dry to wet, and vice versa. The new model is more accurately predicting those transition zones and the positions of those frontal boundaries, and that definitely helps improve the weather prediction at all time scales from the new global model. Improving the wave forecast. For the first time, the GFS is coupled to the global wave model. We know it as WaveWatch 3, which will enable significant improvements to the wave prediction, guidance, and forecasting. The forecasts are extended from the 10 days out to 16 days and integrated them into the global model so that the products are streamlined. The wave and wind forecasts were provided jointly instead of separately. And this also paves way for incorporating future wind-wave ocean interactions for improving the marine weather predictions and the coastal zone predictions due to significant waves. The future, we are moving towards a fully coupled Earth system model. The next version, the GFS version 17, will be fully coupled for both medium range and subseasonal timescales. The schematic that is shown here is a collection of different modeling systems that are part of the Earth system. We have the land model, we have the atmospheric model, we have the aerosol model, sea ice, waves, and ocean models. They're all connected together tightly using more advanced technology and software that allows us to provide more meaningful feedback among all these Earth system components that eventually will lead to even more improved forecasts as we move into the future. We're also planning on extending the forecast out to 1 year using the seasonal forecast system. It will be again fully coupled with reanalysis and reforecasts that will help calibrate the products. And we will also move into advanced coupled data assimilation that takes into account impact of observations in one component of the Earth system on other components. And these implementations are planned for 2024 and 2026 respectively. The unified forecast system is the underlying unifying force in order to bring all the research and operations into one platform. It's a coordinated development of shared modeling and data assimilation infrastructure and algorithms across the entire Earth prediction enterprise. It is open source. Community can access it from the GitHub. Agile development is being approached to make more rapid continuous integration, continuous delivery. We are doing a lot of prototyping and testing. There are unit tests, regression tests, as well as the scientific testing that's happening as we speak. And we are continuously evaluating the results of these new models that eventually will be going into operations. And the Unified Forecast System Research to Operations project is supporting the integration of these new science and technologies into the Unified Forecast System. And we have other programs like the Earth Prediction Innovation Center supporting different research projects at different readiness levels so that they all can eventually find their way into operational implementations through EMC and through National Weather Service. So engaging with the UFS community, there are so many such opportunities. We have increased our partnerships with federal academic research and private organizations. We have the new vibrant community. The link for that community is provided here, ufscommunity.org. So please feel free to reach out to any of us, and we'll be glad to take questions after all the talks are done. Thank you.
Thank you, Vijay, for your very interesting presentation. Next, we have Dr. Robichal Mehra, whose presentation will focus on how NOAA improves ocean forecasting capabilities with upgrades to the real-time ocean forecast system. Please go ahead.
Good afternoon. Good morning to some. My name is Avichal Mehra, and I work as the Chief of the Dynamics and Coupled Modeling Group at the Environmental Modeling Center at Weather Service, NCEP. And today I'm going to talk about improving the ocean forecasting capabilities with some recent upgrades to our flagship real-time ocean forecast system. And thank you for this opportunity for me to talk about this and this important upgrade and to formally be a part of the NOAA Science Report. So a little bit about this forecast system. So this is our flagship ocean operational ocean forecasting capabilities here at NCEP. What the system does is provides us with three-dimensional fields for temperature, salinity, and ocean currents. And the forecast length is out to 8 days. This system is used internally within the Weather Service, within NOAA, to provide inputs to operational hurricane models to help with air-sea wave flux interactions. And as well as it provides inputs to other operational global models like GFS waves, just described by Vijay, and also coastal models like nearshore wave prediction system. And in addition, we provide boundary conditions for multiple other NOAA coastal ocean forecasting systems, which are run operationally by NOS. So the recent upgrade we made to the system, RTOFS version 2, we call it, it's the first operational global data assimilation system at NOAA National Weather Service at 1/12th degree global resolution or mesoscale resolution. So the main motivation for this upgrade was that RTOFS is used regularly by our National Weather Service forecasters at Ocean Prediction Center, National Hurricane Center, as well as the National Ice Center. They're also used by NOAA, National Ocean Service coastal regional forecast systems for predicting tides and currents, as well as by other federal agencies like US Coast Guard for inputs to their search and rescue operations. This update for RTOFS, the science upgrade, includes a formal data assimilation system, which is the first operational global high-resolution ocean data assimilation system at 1/12th degree resolution at the Weather Service. And RTOFS DA here is being used for initializing better and more accurate forecasts for ocean conditions. Further, this upgrade paves the way forward for use of advanced satellite and in-situ ocean observations for future further improvements to operational ocean and coupled forecast systems at the NOAA National Weather Service, including the global systems which are being developed as part of the Unified Forecast System, which was well described by Vijay in the prior talk. So here's a schematic of the data flow through this data assimilation system for RTOFS. This is a complex figure, but I would like for you to focus on the golden box on the left side of this, which lists all the ocean observations which are being used, which include sea surface temperatures, both remotely sensed from satellites like METOP and JPSS, GOES, Himawari, as well as in-situ platforms from ships and buoys. We are also using sea surface salinity data from buoys, as well as from satellites like SMAP and SMOS. All available profile information for temperatures and salinity is also being used including those coming to us from buoys and moorings, as well as new, very modern observing systems like gliders, sea gliders, Alamo floats, as well as sail drones. Another key component of the observing system includes altimeter data for absolute dynamic topography, which comes to us from instruments like JASON, JASON3, Cryosat, Altica, as well as the Sentinel series of satellites. For sea ice concentration, we use AMSR and SSMI datasets, and we are also using velocity datasets from any available ADCP instruments, which are available from ships or from gliders. All these datasets indicated here are brought into the system via GTS, or the Global Telecommunication Service, in real time, and all this data is then ingested to produce the best analysis we can in real time for doing our forecasts. Here are some animations, essentially, which show the drifting buoy tracks. On the left, we have the Kuroshio extension. On the right, we have Gulf Stream. These give us very good, these animations give us a very good idea of the quality of the model surface circulation patterns in the operational system. This is a qualitative way of comparing, but still gives us a good idea as to whether the circulation patterns which we have in our predictions are matching the ones which we can get from observations like drifting buoys. So finally, a little bit on the benefits and the future directions. The main benefit this upgrade provides us is that it gives us much significant enhanced capability to produce high resolution, accurate forecasts for ocean conditions, ocean currents and conditions. It also helps pave the way for future advanced operational both coupled and ocean forecast systems at NOAA National Weather Service. We hope to use more of the marine observations, all kinds, whether they're remotely sensed or in situ, and extract more useful information out of the existing measurements so that we can initialize our forecasts. And we hope that with all these advancements, our future systems will provide even more accurate global and regional forecasts, ocean forecasts, as well as from our coupled systems like our hurricane models, whereby we can provide timely information to our emergency managers for making decisions. And that's all I had. Thank you.
Thank you, Avichal, for that great presentation. Our final speaker is Mark Suttleson, and he will tell us about Merhab, an early warning system for harmful algal blooms on Pacific Northwest Ocean beaches. Please go ahead.
Great, thank you. Can you hear me okay?
Yes.
Excellent. Thank you for the opportunity to speak today. My name, as you said, is Mark Suttleson, and I manage competitive research programs in NOAA's National Centers for Coastal Ocean Science in Maryland. Today, I'll be talking about a NOAA-funded harmful algal bloom forecast pilot program called the Pacific Northwest HAB Bulletin, and sharing how this effort helped the Quinault tribe access valuable razor clam shell fisheries on the Washington coast. Harmful algal blooms, or HABs, encompass a wide range of algal species which can occur naturally in fresh or saltwater environments. Each species can have different causes and different impacts. HABs occur when algae grow out of control while producing toxic or harmful effects on people, shellfish, other animals, or on the environment. Nutrients, sunlight, and water temperature are among the many factors that can combine to create conditions which are conducive to HABs. In the Pacific Northwest, 4 species of HABs, shown on this slide, have historically been of primary concern for managing shellfish. Given limited time today, I'll be focusing on Pseudonychia, its impacts, and the benefits from HAB early warning. Toxic Pseudonychia blooms have caused frequent problems for razor clam fishery managers since 1992, when the toxin it produces was first found in clam meat. These blooms produce domoic acid, a powerful neurotoxin that can build up in shellfish. If people eat toxic clams, it can cause a serious illness known as amnesic shellfish poisoning. Shell fisheries are closely monitored by states and tribes, and when domoic acid levels in shellfish exceed regulatory thresholds, beaches are closed to prevent ASP outbreaks. Monitoring is highly effective at protecting human health. It can take days, months, or sometimes longer for shellfish to flush domoic acid from their systems and be safe to eat again. As a result, HAB-related closures often have negative economic consequences on coastal communities. Advanced warning can enable targeted management actions that protect public health while minimizing societal impacts. Pseudonychia blooms also have broader impacts on regional fisheries. Domoic acid toxicity in razor clams is tightly linked with toxicity in Dungeness crabs, as indicated by the blue and red data trends in the time series shown here. HAB toxin closures of the commercial Dungeness crab fishery can have big impacts. It's the most valuable single species fishery in Washington state, worth about $84 million per year, and is the top fisheries employer in Oregon. Occasionally intense and long-lasting toxic Pseudonychia blooms can have major coast-wide ecosystem implications. Research on a 2015 West Coast-wide bloom linked to a marine heat wave called the blob, and this research documented many notable impacts. For example, the 2015 bloom caused the value of the West Coast Dungeness crab fishery to drop by nearly $100 million. And it also prompted the first ever closure of the region's sardine and anchovy fisheries due to high domoic acid levels detected. Why are razor clams so important in the region? They generate tens of millions of dollars from tourism each year in coastal and Oregon, Washington. Restaurants, motels, and other businesses in coastal communities rely on tourism revenue generated by fall and spring recreational clam digs to bridge the gap between summer seasons. Razor clams are also a culturally important food for the Quinault and other coastal Salish peoples. In fact, a word in the Quinault language, poorly translated as clam hungry, describes a physical, emotional, and spiritual craving for razor clams. Commercial digs provide an important source of income for the Quinault tribe, while subsistence harvests help fill freezers and pantries with nutritious food. To provide an expanded early warning for toxic HAB events and help impacted shell fisheries, NOAA funded a research project in 2016. The multidisciplinary, multi-institution project team has worked closely with regional partners to achieve key objectives shown on the slide. These include piloting a monitoring and modeling-based HAB forecast system, increasing offshore sampling of known HAB hotspots like the Juan de Fuca Eddy and Heseda Bank, and improving Pacific Northwest HAB Bulletin and distributing it regularly to managers ahead of shellfish harvests. The monitoring and forecast system is built on a predictive understanding of the seasonal ecology and dynamics of Pseudonychia HAB events in the region, developed over 15 years of funding from NCOS and other agencies. Researchers like Dr. Vera Traynor of NOAA and Dr. Barb Hickey of the University of Washington and many partners contributed to this understanding, which is simplified in the panels shown on the slide. The project team regularly integrates a variety of inputs to produce each bulletin, including the abundance of algae and toxin in seawater from offshore sampling of hotspots by ships and moored sensors, and from the surf zone by state and tribal scientists. Coastal currents and winds indicate the direction of plankton transport from offshore to beaches, where their growth is fueled by nutrients from upwelling. And modeled predictions of the location and intensity of the Columbia River plume is included, as it can either prevent or encourage the transport of HABs to clamming beaches. The various inputs are then assembled and analyzed to produce each bulletin. The sample here gives you a sense of the bulletin format, which was designed in collaboration with managers. I won't go into all the details, but I've called out the key components, including those described earlier. Bulletins are emailed to state and tribal managers a week ahead of scheduled harvest throughout the spring and fall seasons. Managers also frequently request updates on conditions from the Bulletin team. I'll next briefly describe the example highlighted in the NOAA Science Report. In early fall 2020, Washington and Quinault managers had recorded the highest population of razor clams over the past 30 years. Hopes were high for a return of widely popular recreational razor clamming after COVID concerns had drastically cut the previous year's season. In October 2020, high levels of domoic acid accumulated in razor clams following an intense Pseudonychia bloom. This prompted emergency closures of Washington and Oregon clam beaches, making news in Seattle and local communities. The bloom dissipated in November, but the clams retained high toxin levels for about 6 months, well into 2021, and access to all clamming beaches remained closed. By early spring 2021, toxin levels in clams had finally started to decline, and there was relatively low abundance of toxic Pseudonychia observed along the beaches. In mid-April, shellfish results at Mock Rocks Beach showed domoic acid levels below regulatory limits. This indicated the possibility of a safe harvest before the season ended in May. Clams at other beaches remained toxic. On April 11th, a bulletin was sent to managers providing a risk assessment for the development of new toxic blooms over the next week. With all available information, Quinault managers were confident in approving tribal harvesting at Mock Rocks Beach. Tribal digging there lasted for about a month, and the state also had some successful days of recreational digging. In that brief time, the Quinault commercial harvest netted just under $600,000 for tribal diggers, and a separate subsistence dig provided long-anticipated fresh razor clams and allowed people to stock up on frozen and canned clams. Joe Schumacher, a lead scientist with the Quinault Department of Fisheries, was pleased with the results of the harvest and valued the bulletin. This latest example typifies the success and support for the bulletin within the region. It's helped to prompt targeted intensive shellfish monitoring, allowing for selective opening of safe beaches rather than blanket closures. Another example back in 2017 showed how the bulletin supported a state decision to increase daily limits for recreational diggers ahead of a predicted period of higher HAB risks. This preemptive action resulted in record high tourism revenues and public participation in the fishery. The bulletin system has also increased our capacity to observe and better understand climate drivers of Pseudonychia blooms and predict how climate change may affect future HAB events in the region. The next bulletin is planned for release ahead of mid-April, this coming April's razor clam digs. Active research projects funded by NCOS and partners at IUS continue to develop new sensors and platforms to provide offshore HAB data to the bulletin. Efforts are in progress to sustain delivery of the bulletin, trusted by managers, with support from the Northwest Association of Networked Ocean Observing Systems, or NANUS, and other regional and NOAA partners. The bulletin and related successes are helping shape a new national HAB observing network concept and advancing NOAA ecological forecasting portfolio. Finally, I wanted to acknowledge the many people and partners who have made the bulletin a success and contributed to the example I've highlighted today. Please contact me to learn more about this work or for help in accessing the web links I've provided on the slide here. And I look forward to any questions that people have. Thank you very much.
Thank you, Mark. That was an excellent presentation. And thank you to all our speakers today for your contributions to NOAA science and your very informative talks. Katie, I will now turn it back to you for Q&A.
Great, thank you, everyone. Okay, we're going to ask the questions that came in during the presentations, and if you have a question right now, please feel free to add that to the chat. So first up, I have a question for Vijay. Is the GEFS V13, version 13, I'm assuming, still planned to be implemented at the same time as GFS version 17?
Yeah, that's a great question. Thank you for asking that. Yes, the plan is to combine the deterministic and ensemble components of the global forecast system as a single entity with slightly different configurations as required. But the plan is to implement GFS version 17 and the GEFS version 13, same time in 2024.
Thanks, Vijay. We also have one more question for you. How many vertical levels does the model have now after the upgrade? And could you talk about how this alone improved the forecasts?
Another great question. We doubled the vertical resolution from 64 to 127. That's like adding more horsepower, more granularity in the vertical. And the vertical levels are staggered in such a way that you provide more resolution both in the lower troposphere, where it matters to those who are living on the ground, and also in the stratosphere, where there is a strong influence of that weather at the stratosphere on the ground too. So we optimized the vertical levels in such a way that we discretize the atmosphere in much more granular details. And the improvements, most of the improvements that we have seen, particularly in the precipitation forecast, as well as the general dynamical variables, they are coming from the vertical resolution alone. Obviously, the physics has to be optimized for the newer vertical resolution and also include more stratospheric physics because we raised the model top. But I think doubling the vertical resolution, which we have not done in the last 18 years, is a great and more significant improvement in GFS version 16.
Wonderful, thank you. We have a question for Avichal. Does the model feed into the Chesapeake Bay? And if so, how is it used for the local Washington, D.C. forecasts?
Yes, so it's a global model, RTOFS. And as I mentioned during my talk, we have a number of NOS, high resolution coastal models, which take in the initial conditions and the boundary conditions from RTOFS. So improvements to RTOFS impact these local high resolution coastal models like for Chesapeake Bay run by NOS. And hopefully by providing better boundary conditions and initial conditions for circulation patterns as well as hydrography, meaning temperature and salinity, three-dimensional information, these would lead to further improvements in the coastal models like that for Chesapeake Bay. And this should help the physical circulation patterns as well as the downstream applications for using the physical information for any ecosystem forecasts like for HABs or red tides or hypoxia or for fishery assessments.
Thank you, Avichal. If you have a question, please place that in the question panel. In the meantime, I'm going to ask a question of all the speakers, and you guys can take turns. What is something you didn't get to say in this quick 8-minute presentation that you wanted to add on? And I'm going to start with Amy.
Sure. So I guess if there's a question I get a lot, it's, do we expect Arctic cold air outbreaks to increase with climate change? And my general response is that there's a lot we don't know, but that overall what we do know and that all the models agree on is that things are going to get warmer over time, and winter especially has been the fastest warming season in the United States. So generally we'll expect to see these colder outbreaks occur less often and be less severe. And you know, its links to the polar vortex are very interesting, and I think there's a lot of research still going on to try to understand how the polar vortex will change in the future as well.
Thanks, Amy. Kyle?
Yeah, hi. I would just highlight the fact that in atmospheric science, we've really only begun to scratch the surface of possibilities when it comes to machine learning. And so I think as we continue to develop our capabilities and explainable and interpretable techniques, I think we'll see more use of machine learning as it enables being able to do more with less computational cost.
Thanks, Kyle. Mark?
Thanks. Sorry, had some little trouble with the mute. Katie, thanks. Yeah, I would say that one of the challenges that we face within the world of harmful algal blooms and trying to provide mitigation solutions is that each region has a variety of HABs that are causing problems, and the solutions are different. And so the model needs, the observing needs, and all of those capabilities that I've touched on in this particular region sometimes will work in others, but often do not. And so we are working, we do have an operational forecast capability that's being stood up in NOAA for harmful algal blooms. And we're working on standing up an similar observational capability as well. So those are interesting and exciting opportunities coming forward. Thank you.
Thanks, Mark. We did have one more question come in, and this one is kind of open to everyone, so I do want to ask it. Can someone speak to the advancements in data assimilation of satellite information related to surface parameters, like SWE, vegetation health, and soil moisture as part of the NOAA land surface model component, and hence impacts on hydrology challenges? So Vijay, Avichal, Kyle?
Yeah, I can definitely speak for it. That's a wonderful question. We traditionally were not able to use the land surface data sets in our assimilation and for its full potential. And there are active areas of development through Joint Center for Satellite Data Assimilation and a bigger collaboration with NCAR, NASA, and NOAA to increase the use of observations, particularly the vegetation fraction, the green, the GVF, and the soil moisture, the SMAP. All these data sets are now being actively pursued to initialize NOAA land surface model. We are moving towards NOAA MP as our next future land surface model for all our applications. And these efforts are leading towards better initialization of the soil moisture, soil temperature, and other land characteristics that definitely will help improve surface forecasts going forward. Thank you.
Thanks, Vijay. And we are right up on time. We're actually a minute over. So I want to thank all of our speakers today and all of our attendees. Thank you for joining us. We did record this. It will be up on the library's YouTube channel later. And please tune in for the next presentation, which will take place on March 23rd. And that will be our fifth and final one on sustainable use and stewardship of ocean and coastal resources. So please be on the lookout for the registration for that. Thank you all, and I hope you have a safe and healthy rest of your Wednesday.